we were here on the middle of an example, and we are approaching the end of chapter 6. We're going to finish chapter 6 today. All right, chapter 6 today. So I might go as far as to say we can have the chapter 6 test Friday, right? So we'll count on that, and I'll put a slide in here. Let's just put a slide in here. Right. Chapter 6 test, Friday, right? 1:29. And I mentioned last time that it was either going to be Friday or the following Monday, but we're going to finish today, chapter 6. And so that we'll do that on Friday. We also have the quiz that was supposed to be today, which obviously won't be today, so we'll have that tomorrow, right, on chapter 5, transcendental derivatives, okay? Going back, we were in the middle of this example, and it was a first-order linear differential equation. And our first step in one of those is to write it in the proper form. So this is step 1, is you write it in the proper form. Write in proper form. 2, you compute u of x, right? And u of x came here to in this case, came to x squared plus 1 to the 3 halves. And now step 3, you plug it into our general formula, which is, let's see here. Our general formula is y equals 1 over u of x integral q of x u of x dx. Right. So in our case, our q of x is right here. Keep that in mind. 6x over x squared plus 1. So that's going to be 1 over u of x (3 halves) integral q of x. Q of x is 6x over x squared plus 1 times x squared plus 1 3 halves dx. You can hear the snowplows coming by. It's there's nothing out there that you really want to go out for today. I'll tell you that the roads are absolutely covered. All right. Down here. Wait a minute here. Jesus. He went away. Okay. Jesus. How's it going? It'll work better if you log in from your YC account, but I let you in anyway. Hopefully you can hear me. Okay. Just a quick reminder. We're going to finish chapter 6 today. Chapter 6 test is this Friday. I mentioned last Friday. It could be this Friday or the following Monday. So we're going to finish today. That gives you several days to prepare. And we're going to have the quiz that was going to be today. It's going to be tomorrow in class over the derivatives of transcendental functions. We were working the problem that we left off with last time. Plugging into that final form, we have this. Now, let's see something here. Yeah, okay, good. So this is something that you need to be able to integrate. This is why I'm practicing. I got you practicing derivatives. And I will say, I hope each one of you spent time this weekend, a fair amount of time, practicing those derivatives. So we've got to be able to integrate, perform this indefinite integral. The first thing I would see is that this is x squared plus 1 to the first. That's x squared plus 1 to the 3 halves. So that entirely cancels with that. Leaves a 1/2 there. And we're ready for a pop quiz. You ready for a pop quiz? Pop quiz time. Ready? We're going to have 1 over x squared plus 1 to the 3 halves integral. Actually, we're going to bring that 6 out. So we'll put the 6 up here. Make that a 6. Integral x squared plus 1 to the 1/2 dx. Pop quiz. What is this integral? It's in a basic form. It does not take too much manipulation. I'm going to give you, I'll give you 30 seconds to see what you come up with. All right. I'll give you a hint. You should be thinking U substitution, if that means anything to you. All right. What you have here is you have a function U to a power. U to the 1/2. You need the derivative of the inside on the outside. So using U substitution, and by the way, I've mentioned before, this is one that if you've done a few of these and you're at where you should be for Calc 2, you may not even need to actually do the substitution itself, but I'm going to do it. We're going to let get rid of the yellow first. Let U is x squared plus 1. Du is 2x dx. And so we have here x dx is 1/2 du. This is chapter 4, one of the last sections of chapter 4. So that particular integral, using U substitution, is 6 x squared plus 1 on the outside, 3 halves, doesn't change. And what you have inside here is integral x squared plus 1 to the 1/2 times x dx. So this right here is U to the 1/2. This right here is 1/2 du. Right? And so that gives you 6 x squared plus 1, 1/2. Integral u to the 1/2 du, and we have a 1/2 on the outside. And I'm gonna put this 1/2 right here on the outside, right there, 1/2. Okay. That gives us what? That cancels, which is 3 up top. This integrates to 3 x squared plus 1, 1/2. And I'm going to have u to the 3/2 power divided by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So this is going to be 2/3 times 3 x squared plus 1, 1/2. And then that is going to be u to the 3/2. Now it's time to re-substitute. We re-substitute. And that we put this back in for u. This comes back in for u. Right? Those cancel. So you have 2 x squared plus 1, 1/2. Oh, you know what? Typo. That's to the 3/2. This right here is a 3. 3 from this up here. And I have another one over here I missed. See, I just copied that wrong. And then I'm going to have what u is. U is, one important thing here. Yeah, I'm going to have x squared plus 1 to the 3/2 plus c. Right? We're going to add our c on the end of that, and if you wanted to, you could add a c right here. Right? So we're not done yet. We got to simplify. We multiply. This has to be distributed over those two terms. So we're going to have at the beginning 2 over x squared plus 1 to the 3/2 times x squared plus 1 to the 3/2 is just a 2. And then I'm going to wind up with 2 over x squared plus 1 to the 3/2 times this constant. Let's call this one C1. And then this term times C1 is going to give me a different constant on the top. So that's going to give me a different constant. I'm going to call it C over x squared plus 1 to the 3/2. And that is our solution. That is our solution. I cannot underscore the importance of being able to integrate something like this. Because this is a very straightforward use substitution problem. And if you need review on that, at the end of chapter 4, I think it's section 4.5 or 4.6 is where you need to go for review. Let me see here. That will be, I'm looking it up. 4.5, section 4.5. So if you need to work these kinds of problems, this is section 4.5. Get in there and do some problems. All right. Let's go back through, and I want to figure out, I want to allow you to, any questions you might have. We started this back on Friday. The first step was to get our original differential equation. This differential equation, we had to get into standard, proper first order linear form. And this became P of X. This became Q of X. All right? And this is the standard form right here, right? So that is your first step. The hardest part of the test on Friday is going to be, the hardest part of the test on Friday is going to be recognizing differential equations for what form they could go in. Our choices are separable, homogeneous, first order linear. And you need to know how to proceed in each one of those cases. We saw that the homogeneous case can actually be fairly lengthy. All right. This here is long enough, but the homogeneous case can be fairly lengthy. And so that is going to be the one stumbling block. If you went to tackle this by separable, this differential equation is not separable. You could try to separate it, put the x's on one side, the y's on the other. But everything you're going to see is going to be in one of those three forms. All right. Keep in mind, for homogeneous differential equations, once you show that the differential equation is homogeneous, the substitution that y equals vx, that will turn that differential equation into a separable one. But it's lengthy, and then you have to resubstitute back in further down. So anyway, so you write it in proper form. Then once you do that, you calculate your u of x. U of x is e to the integral p of x dx right here. We've done this a few times. On Friday, we did this. We integrate. You had to perform this integral here on Friday. All right. So you have something in the top that can be made into the derivative of the bottom. That comes out to log of the bottom. Then you have this 3/2 up front. That 3/2 up front goes up top here as a exponent. And then e to the natural log of anything is the anything. So this is our u of x. 1 over u of x gave you this, is 1 over u of x. And then here you have q of x times u of x. You do some simplifying, you wind up with the integral in the yellow. I've already told you, you must be able to integrate basic stuff like that. In doing so, I chose to use u substitution. U substitution is more steps than I would use personally, but I wanted to review u substitution with you. And you wound up with, you let u usually be whatever is inside. So this right here is what would be normally u. Whatever's inside, let that be u. And so that whole first term comes out to u to the 1/2. This is 1/2 du. And again, section 4.5, if you cannot do that fluidly, right? You wind up with the integral. Down here, you resubstitute back in. You have this. And then you got to simplify. You have to distribute this expression on the outside. It has to be distributed inside. And you get your final answer. Questions? Questions? Moving on. Here's some love for, we'll make this one for Wednesday because tomorrow you have your quiz. But this one is, of course, this is going to be first order linear because it's in the first order linear section. But there is a first order linear differential equation. There's a solution, right? What I expect from you is the work. Now, you're going to have another differential equation due Wednesday. And it's going to be one of these. It's going to be one of these. Some kind of applied differential equation. One application of differential equations that's very common is mixture problems. Mixture problems. And mixture problems where you have some kind of mixture in a tank. You've got something going into the tank and something going out of the tank. All right. Actually, you may not have something going out of the tank. It doesn't have to be, but a lot of times there is something going out of the tank. And these are an application of differential equations that you see very much in the real world. This is a fairly straightforward one. I hope you can follow it. All right. You will not understand it the first time through. You will not understand it the first time through. You got to go through several times. But a 120-gallon tank initially contains 90 pounds of salt dissolved in 90 gallons of water. The brine containing 2 pounds of salt per gallon. Brine means salt water. That's all that means. Water containing 2 pounds of salt per gallon flows into the tank at a rate of 4 gallons a minute. And the well-mixed solution, so it's getting mixed up, flows out of the tank at 3 gallons per minute. How much salt does the tank contain when it is full? Okay. So you have a 120-gallon tank with 90 gallons in it. All right. So you go over here. My recommendation is to make a drawing of the 120-gallon tank. Okay. So that's our 120-gallon tank. 90 gallons is currently in the tank. All right, so 90 gallons. Like that. Right? It's what, 3/4 full? Now brine is going into the tank at 4 gallons per minute, 2 pounds of salt per gallon. So into the tank is flowing water, brine, and this is 2 gallons per minute. And it has, make that 4 gallons per minute. And it contains 2 pounds per gallon of salt. All right. Water is flowing out of the tank. So down here you have water flowing out of the tank. At 3 gallons per minute. And so it's mixed. All right. How much salt does the tank contain when it is full? When it is full. Now, let me tell you the way I approach these problems. There may be another way. Oh, I should mention, for these differential equations you're going to have to do, I told you you're going to have to recognize what kind they are. Sometimes there's more than one. A particular differential equation can be solved in more than one way. Sometimes it could be first order linear or let's say homogeneous. That could happen. So either way that works, you'll get the same answer or an equivalent answer, right? So here is a key. You ready for a key? Let your variable y of t, so your two variables are going to be y or some variable, pick it, and t for time. So you're going to let y of t be the pounds of salt in tank at time t. Not the gallons, how much salt? Salt. All right. Now we're going to have to go up here. We're going to have to go up here and identify, this is also key, two things. What are you given? And what do you seek? We are given how many gallons or how many pounds of salt that are in the tank at t equals 0. So we're given that y of 0, you're told that y of 0 is 90 pounds. We seek y when the tank is full. Now, how long will it take to fill the tank? Well, you have 90 gallons in it now. Here, let's just do this. This whole thing is 120 gallons. You presently have 90 gallons of solution in there. It's going in at 4 gallons per minute. It's coming out at 3 gallons per minute. So it's coming in, it's going in faster than it's going out. It's going in at 4, coming out at 3. So the tank gains 1 gallon per minute. Going in at 4, coming out at 3. The amount of liquid, the amount of brine in the tank is increasing at 1 gallon per minute. You know that you have 30 gallons up here. There's 30 gallons of space in the tank. If it's increasing at 1 gallon per minute, it is going to take 30 minutes to fill the tank. 1 gallon a minute is how much it's increasing by the liquid in the tank. If there's 30 gallons of empty space, it's going to take 30 minutes. This stuff in red is critical. That's why I put it in red. That is critical. Now, okay, any questions on the setup? I know that's a lot. And honestly, if you're behind in the kinds of differential equations and stuff, this might even be a fog. I hope it isn't.
Why 30 instead of 120?
Well, 120 would be if the tank were empty. right? You only have 30 gallons of space in it that is empty, right? And so there's 90 gallons of something else already there. So to fill up the 30 gallons of space, the amount of liquid in the tank is increasing at 1 gallon per minute. That's 30 minutes. Because it says you want to know how much salt does the tank contain when it is full. So that amount equals this. Y of 30. It'll take 30 minutes for the tank to get full because there's only 30 gallons of space left in it. Okay, now here's my next pointer to you. We're going to set up a differential equation. And this right here is the test whether somebody understands differential equations or not. Right? So we're going to let the change in y with respect to t, that's y prime, right? The change in the amount of salt. So we're going to track the salt. The change in the salt is going to equal the incoming salt minus the outgoing salt. Right? That's the change. Incoming minus outgoing. Now, if you've had any physics, if you've had any chemistry, that will come in handy now. How much salt is coming into the tank? How much salt is coming into the tank? Well, there are 2 pounds per gallon. That's how much is in, that's the concentration of the salt in the incoming fluid, brine, times 4 gallons per minute. So this is how much salt per gallon. That's how many gallons per minute. Notice those two change. Oh, excuse me, cancel. And so the incoming salt is 2 pounds per minute. Do both of you understand that? It's sort of like you're going 60 miles an hour for 1.5 hours. I'm going to write this and then 60 miles per hour for 1.5 hours. Right? That would be, those cancel, and that would be 90 miles. Sort of similar to that. That is your incoming salt. What is the outgoing salt? And this is the hardest part. What we're about to write is the hardest part. You're going to subtract off the outgoing salt. How fast is it going out? 3 gallons per minute. Right? That's how fast it's going out. What is its concentration? Its concentration is how much? Well, concentration is the amount of salt in the tank divided by the volume of the tank. Concentration is how much salt is in the tank divided by the volume, meaning not the volume of the container, the volume of water in the tank. So the amount of salt in the tank at any time is Y. The amount of liquid in the tank is how much? 90 is how much you start with, right? By how much is the volume of liquid increasing per minute? It is 1 per minute, 1 T. So after 2 minutes, 92 gallons in the tank. Right? And the units on that are pounds per gallon. Once again, and this is a test to see if you set it up right. This is a test. Gallons cancel. So you should have the same units on the first term as the second term. Same units on the first term and the second term. You can't subtract them unless they are the same units, right? You can't subtract number of eggs from dozens. No, you got to do dozens or convert them both to the number of eggs, right? You can't subtract pounds from kilograms. You've got to convert them both to pounds or both to kilograms. So the key step here is the one that people, I think, most often trip on is this. This right here. I'm going to make it bolder. Okay, that's a key one. Once again, you want incoming salt versus minus outgoing salt. The amount outgoing it's going out at 3 gallons per minute. How much salt is in the tank at any time? Y divided by the concentration. Well, divided by the volume. The volume is 90 plus 1 gallon for every minute. So this gives you the pounds of salt per gallon. That's the concentration. That's the concentration. That is probably, this is the all-star step right here. If somebody can set this up, you're home free. Right? Now, what kind of differential equation is that? What kind of differential equation is that? Is it separable? Is it homogeneous? Is it first order linear? Well, let's see. Over here, I have y divided by this thing here, this 3y. If I put that over on the left side, I would have dy dt. Put this on the left side, I would have 3 over 90 plus t times y. That's this one here. And that would equal 2 times 4 or 8. So this goes here. And we have a frozen board. Oh dear. Let's hope this didn't see it. Oh, not so bad. Not so bad. Not so bad. We lost a little bit. But what do we have here? Let's put the dy dt plus 3 over 90 plus ty equals 8. And what I had written there before is that this part here goes to here. And then the 2 times 4, this whole part here, equals 8. Notice on this first term, notice on this term right here, there are no variables, no t's or anything. All right? So let me move it now. Okay? So that buzzard right there, that thing, is what kind of differential equation? First order linear. This is P of X. That's Q of X. And so we know how to solve first order linear, right? What's step 1? Get it into the form. Step 2, compute U of X. So this is step 1. Step 2, U of X is what? E to the integral P of X dx. That is e to the integral. I'm going to put the 3 on the outside. 1 over 90 plus t dt. Pop quiz. Pop quiz. What's that integral? What's that integral? Natural log. The top is the derivative of the bottom. You don't have to do anything to that. That's going to be, oops. That's going to be e to the 3 natural log 90 plus t. Now in this case, 90 plus t is greater than 0, right? Because t is positive. So this equals e to the natural log, e to the natural log 90 plus t cubed. And you're probably tired of seeing it, but e to the log of anything is the anything. So this is 90 plus t cubed. That's our u. What is our y? Now these first order linear, this process, it looked like Greek when you first do it. But if you do a few of these, you'll know the next step. I promise you will. Because the next step here is y equals 1 over u. That's u. Right? There's u of t. And I made a little mistake here. This should be u of t, not x. All these should be t's. All of them are t's, no x's. Then this is 1 over u of t integral Q times U. Q is 8. U is 90 plus T cubed dt. Okay. So what's that going to be? 1 over 90 plus T cubed. Brackets. Pop quiz. What's the antiderivative of that? This is a straight up U substitution. This is a U. Du is 1 dt. Okay. So this 8 can come all the way out here. So let's make this an 8 out here. And this is going to be what? This to the 4th power divided by 4 plus C. So it's going to be 1/4 90 plus T to the 4th power plus C. And that is going to equal 2 times, because the 8 divided by 4 is a 2, 90 plus T, plus 8 times C, call this a C1. 8 times C is a C divided by 90 plus T to the cube. That is our solution to the differential equation, but that's not the solution to our problem. I want to stop here and ask if both of you understand the steps we did here. We have this first order linear differential equation here. We identify P, identify Q. Step 2, this is step 3 down here. Step 2, U is e to the integral pt dt. That comes out to be 90 plus T cubed.
Why you put 1/4 and to the 4th power again?
Okay. Because of this. Because of this. That is of the form, that has the form u, some function to the 3rd power, right, du. And so that integral is u to the 4th over 4 plus c. That's once again section 4.5. Integration by substitution. So anything to a power times its derivative. You take the anything to the next higher power, divide by the new power. That is that's section 4.5. I would go back and work a bunch of those if that is foggy to you. Right? So we're going to go, we have this is a solution to our differential equation, but we're not done. We're not done. You see right here, we have this C. In order to answer our question, we have to solve for C. And in order to do that, you need something called an initial condition. But going back up to the top, this right here is our initial condition. We know that, so here, our step here, step 4, if you will, we're going to use the initial condition. Y of 0 is 90. And so what we're going to do is we're going to plug in we're plugging into our differential equation, y of 0 equals 2 times 90 plus 0 plus c divided by 90 plus 0 cubed. That has to equal 90. So our initial condition says y of 0 on the left equals 90. And that's going to give me 2 times 90, 180, plus c divided by 90 cubed. Solve for c. So what do we have? C divided by 90 cubed is going to be 90 minus 180, which is minus 90. So C equals 90, minus 90, excuse me, to the 4th power. C is minus 90 to the 4th power. Now, I don't want to lose this. I'm going to save that again. Get out of it. Back in it. All right. I'm going to take this part, go to the next page. Step 4. Right? So that is C is minus 90 to the 4th. So our differential equation, y equals what? It's going to be 290 plus t plus negative 90 to the 4th divided by 90 plus t cubed. All right. Yeah, we're good. Almost done. What are we seeking? You remember at the very first step, I said given and seek? That's very important to identify what information you've given and what is it you're actually looking for. What I'm looking for is y of 30. That's going to be 2 times 90 plus 30 minus 90 to the 4th divided by 90 plus 30. So this is going to be, wow, 2 times 120 is 240 minus 90 to the 4th divided by 120 cubed. You should be able to simplify that. You should be able to simplify that. Let me see here. This is going to equal 240 minus 90 to the 4th is 3 to the 4th times 30 to the 4th. 120 cubed is 4 cubed times 30 cubed. So what you're left with here is that cancels with that, leaves a 1. And so that's going to be 240 minus 3 to the 4th is 81. Right? 81 times 30. 81 times 3 is 243. So this is 2430 divided by 4 cubed is 64. And that actually reduces some, doesn't it? Yeah, that reduces. That's going to be 24 minus, top and bottom are divisible by 2. So that's 1215 over 32. On a test, that's your final answer. That comes out to be around 202 pounds of salt. All right. There are examples like this in the book. There's plenty of examples like this. If you want extra problems to solve, you can YouTube almost any topic. You can put mixture differential equation. It'll come up. First order linear differential equation. Examples come up. Solved. I of course recommend Khan Academy. It's kind of my #1 site. Just put, homogeneous differential equations, and you'll have examples there that are worked out on video. You can pause the video, and they also have problems for you to work on. But first of all, I would work with the problems in the book. I'm going to walk through this one more time. Stop me with any questions, right? The key part here is at the beginning. If you mess up this first part, you're going to be off in la-la land down here. Total la-la land, right? So if you practice anything, practice setting up these word problem differential equations until your fingers are raw and bleeding. Okay? Practice these. I gave you definitely my strategy. When any of these mixture problems, I would tell you, let your variable y be the amount of whatever in the liquid. In this case, it's salt. It could be something else, right? I recommend drawing a little drawing of in this case, of the tank to give you an idea. You have 4 pounds per gallon coming in at a certain rate. You have 3 gallons a minute going out of whatever's in the tank. Right. And so from there, you're setting up a differential equation. Oh, very important right here. You write down the information you are given in the problem. You're told that there are 90 pounds of salt in the liquid at the beginning. So y of 0 is 90. It's asking for how much salt is in the tank when the tank is full. You figured out that there's 4 gallons a minute going in, 3 gallons a minute coming out. So there's 1 gallon per minute being added to the tank, to the 90 gallons that are already in the tank. The 90 gallons are growing by 1 gallon a minute. Next. Okay, so from there you can formulate what you're after. You seek y of 30, because 30 is how many minutes. It's how many minutes it will take to fill the empty 30 gallons at the top of the tank. That's where we get that from. So this part up here, right? Es muy importante. That's the key. That's the key to the whole thing, which might be why I put key on the outside. Just about as important is this, because that's setting up your differential equation. You're going to track the amount of salt. And the amount of salt, the change in the amount of salt, excuse me, is the amount of salt going in minus the amount of salt going out. I went through this before, but the amount of salt going in, it's coming in at 4 gallons a minute, 2 pounds per gallon. That gives you a nice even 2 times 4 or 8. Right? And then you have 3 gallons a minute going out. And this right here is, I told you, is probably the trickiest single thing, but it's not that bad. Because you need the flow rate going in or out, and you need the concentration going in or out. The flow rate going out is 3 gallons a minute. The concentration is Y, your variable. That's how much salt is in the tank at any time, divided by the volume that's in the tank, which is 90 plus 1 T. 1 gallon for every unit of time T. We scramble things around just a little bit. The dy dt goes here. We put that there, which I already had. And then you have this comes to here, it just means it's just a nice even 8. That you have to be able to recognize as a first order linear differential equation. Right. First order linear. We are out of time. But for first order linear, you apply what you know. You calculate your u. You plug it into the formula. Y equals 1 over u. Q times u, integral q times u. You've got to be able to integrate what you get with q times u. And honestly, that is a concern of mine for the two of you. Can you integrate that? That is not a hard antiderivative. But do yourself a favor, go back and learn that u substitution, section 4.5, which I've been saying all along. And this is the general solution to our differential equation. You then use the information you're given. You're using this. That's your initial condition. You use that to find C. You wind up with C being minus 990 to the 4th power. And so this right here is our differential equation. All we need to do is evaluate that at 30. After 30 minutes, the tank is full. And that produces this many pounds of salt in the tank when it is full. All right, I'm going to leave it there. I'm going to shut off the recording.